A universe teetering on the brink of oblivion, where the relentless pull of dark energy threatened to snuff out the fledgling sparks of creation before they ever had a chance to ignite. Yet against all expectations, our universe persevered, birthing galaxies, stars, and the cradle of life itself. Join us as we delve into the depths of this enigma, uncovering the secrets that have shaped our reality since time immemorial. From the primordial chaos to the symphony of celestial bodies dancing across the heavens, every step of our journey unveils the intricate design of the cosmos. But pause for a moment and ponder this profound question. Are we merely cosmic accidents adrift in an uncaring void, or is there a higher purpose guiding our celestial odyssey? Before we dive into this journey, a humble request: hit that subscribe button to stay updated on all things space-related. In science class, they talk about gravity, the invisible force that brings objects closer together. It's what keeps planets in their orbits around the sun and holds stars together in galaxies. But when we zoom out and look at the whole picture, we notice something odd. Instead of moving closer, groups of galaxies are actually moving farther apart from each other. So, what's really going on here? In simple terms, gravity usually brings things together, like when you drop a ball and it falls to the ground. But on a cosmic scale, it seems like something else is at play. Instead of gravity pulling everything in, it's like there's a mysterious force pushing things apart. It's as if the universe is expanding, stretching out like an inflating balloon. Scientists have been scratching their heads over this for years. They've come up with a few theories to explain this strange behavior. One idea is that there's something called dark energy, which acts like anti-gravity, pushing things away from each other. Another theory suggests that the universe is just so vast that gravity can't overcome the expansive force, causing everything to drift apart. Einstein's theory of general relativity provides a fascinating way to understand this strange phenomenon. In general relativity, space isn't just a passive stage where objects move around. Instead, it's a dynamic arena that can stretch, twist, and evolve over time. Einstein's brilliant idea was that gravity isn't like a force that pulls things together, it's more like a bending or warping of the path objects naturally want to follow through space. For instance, when a planet orbits the Sun, it's essentially traveling along a straight line in a curved space created by the Sun's mass. Similarly, when we see galaxy clusters moving away from each other, it's not because something is pushing them apart directly. Instead, it's like the space between them is expanding, causing them to move away from each other. But why is space stretching out like this on such a grand scale? To answer that, we need to dive deeper into what causes space to bend and stretch in the first place. Einstein's theory suggests that space itself can stretch and warp in response to the presence of mass and energy. This stretching of space is what we perceive as gravity. Imagine a rubber sheet with a heavy object placed in the center. The sheet curves around the object, creating a gravitational well that pulls other objects toward it. But here's where things get really interesting. Not only can space stretch and warp, but it can also do so at an accelerating rate. This means that the expansion of the universe is not only happening, but is also speeding up over time. This discovery, made in the late 1990s, was quite unexpected and has led to even more questions about the nature of our universe. So what's causing this accelerated expansion? Scientists have proposed the existence of a mysterious energy called dark energy. Dark energy is thought to fill all of space and exert a repulsive force, pushing galaxies away from each other and driving the universe's expansion to accelerate. In Newton's gravity theory, objects with mass create gravity, while in Einstein's general relativity, mass also curves space-time around them. Einstein showed that besides mass, any form of energy or pressure affects spacetime's dynamics. Energy density measures how much energy fills a space, like heat or motion. In our universe, it's always positive. Pressure measures the force over an area that pushes into space, like interstellar dust bumping into each other in the void. For distant objects, this pressure value is tiny on a cosmic scale, hovering slightly above zero. When energy density and pressure add up to be positive, they make space contract, creating gravity. But if pressure is negative and greater than positive energy density, the equation flips. This could accelerate space's stretching, creating something like anti-gravity, dark energy. Visualizing negative pressure is tricky. It's hard to imagine having fewer than 0 atoms in a space. Atoms aren't the only things that create pressure. Fields can too. Imagine a magnetic field pulling iron toward a magnet or two magnets repelling each other. If dark energy were a field pushing everything away, it would explain the universe's gentle expansion. Scientists have studied dark energy and figured out its energy density and pressure needed to create the observed spatial expansion rate. It's a very small number, around 10 circumflex 9 in SI units. We don't usually notice it on Earth, only on the vast cosmic scale. This is actually good news, because if the number were much higher or lower, things would be bad for our existence. Here's a quick sketch of the universe's history from just after the Big Bang to now. This line represents the dark energy density measured by astronomers. Scientists think its negative pressure has kept this density roughly the same for billions of years. This line shows the density of ordinary matter in the universe, which has little to no pressure. Over time, the density decreases because the universe expands and spreads out the matter. This line represents the density of radiation in the universe, including photons and other light particles. Radiation's positive pressure causes it to dilute away even faster than ordinary matter. In the beginning, there weren't any atoms, but soon, protons and neutrons joined together to make the first atomic nuclei in the early universe. After that, matter became the main type of energy, beating out radiation. As the universe cooled down, nuclei grabbed onto electrons, making the first hydrogen and helium atoms. Imagine if dark energy's push was stronger. It might have stopped galaxies from forming in the beginning, pushing stars apart more than gravity could pull them together. If it was a bit stronger, stars might have had a hard time forming at all. And if dark energy was even stronger, hardly any atoms or nuclei would have formed in the universe. So that's what could have happened. As we reflect on the sheer improbability of our existence in this vast universe, one can't help but wonder, how did it all happen? Was it mere chance, or is there something more profound at play? We'd love to hear your thoughts. Leave your theories and musings in the comments below. Let's spark a conversation and dive deeper into the mysteries of our existence. And remember, if you're as fascinated by space science and education as we are, don't forget to hit that subscribe button. Stay tuned for more thought-provoking videos exploring the wonders of the cosmos. See you in the next installment.